welcome back. So to start things off, let's do a quick recap on the things we talked about last time. So our discussion is going to be on the unit circle, which is a circle of radius 1, centered at the origin. So I can label this point 1, 0, and we understand this is 0, 0, 0, 1, etc. And then we make angles in the standard position. So we say, okay, the initial side of the angle is going to be the positive x-axis, and then we can say, if I go counterclockwise to there, that's a positive angle with measure t. And this terminal side is going to intersect the circle at some point. We can label this P with coordinates x and y. And the unit circle definitions of the trigonometric functions are that the sine of the angle t is going to be the y-coordinate of the intersection of the terminal side and the unit circle. And then cosine of t is going to be the x-coordinate of that intersection. And then tangent of t is going to be the y-coordinate divided by the x-coordinate here. So we can look at this and say, oh, tangent of t is actually sine of t divided by cosine of t. And this is going to be true for all values except where cosine of t is 0. So you can think of this as what we call an identity. That means this is true everywhere that the expression on the left and the expression on the right are both defined. Okay? Then I can continue and say there were 3 more trigonometric functions. There's cosecant of t, which is 1 over y, and we see these are related by a reciprocal relation. So we can say that cosecant of t is actually 1 over sine of t. This is another identity. We define secant of t as 1 over x. And so in this case, we would say that secant of t is equal to 1 over cosine of t. Once again, a reciprocal relationship. And then cotangent of t is defined as x over y. So we can understand this as cotangent of t is equal cosine over sine, so it's cosine of t divided by sine of t. And then this is the reciprocal of that. So we could perhaps write that cotangent of t is equal to 1 over tangent of t. And these are all what we call trigonometric identities. These we call quotient identities because you form them by a quotient, and these we call reciprocal identities because you form them by a reciprocal. And in red, I'm going to come through and say there are other ones we can write that are perhaps less used, but true nevertheless. So I can take this and say, what if I reciprocate both sides? I would end up with sine of t is equal to the reciprocal of cosecant t. So these are reciprocals of each other. Similar business with the cosine and the secant. Cosine of t is 1 over the secant of t. And then tangent of t is 1 over the cotangent of t. And based on these relationships, I could say, oh, well, since sine of t is 1 over cosecant of t, and cosine of t is 1 over secant of t, I could similarly write tangent of t as secant of t over cosecant of t. And then I could write cotangent of t as the reciprocal of that. That would be cosecant of t over secant of t. Now, naturally, the question arises, is it important to memorize these things? And I would say there are certain ones that you should definitely memorize. For example, this one comes up so often. So does this one. And so does this one. And so does this one. I think these are worth knowing well enough that you don't even have to think about the word memorize anymore. The other ones, they're good to know. And in fact, you can rederive them very quickly if you have the boxed ones solid in your mind. So I would say either remember these or force yourself to remember that tangent is a quotient and that cosecant, secant, and cotangent are all reciprocals of the other trigonometric functions. When I first learned this, the way I kept this straight in my head was to say that in every reciprocal pair, there's only one function that has a co in its name. So cosecant is a reciprocal with sine, cosine is a reciprocal with secant, and cotangent is a reciprocal with tangent. Maybe that's useful. Now, equipped with these definitions, we could look at something like you see in the calculator display and say, for the angle 2.1274 radians, I could write sine of 2.1274, and this would be the y-coordinate of the intersection point. So you can see the coordinates here of that point. this would become 0.84907. And keep in mind, this is a rounded quantity. I only have the calculator set to display 5 decimal places, but this number does keep going. I could write cosine of 2.1274, and this would equal negative 0.52828, the x-coordinate of that intersection, once again rounded. And then I could write down the tangent of 2.1274, and this would become the value of sine divided by the value of cosine. So I'm going to go ahead and just write this as 0.84907 divided by negative 0.52808, and we can calculate this later if we really need to. Cosecant of 2.1274 is equal 1 over the sine of 2.1274, because sine and cosecant are reciprocals. So I can write this as 1 over the y-coordinate. Then secant of 2.1274 is equal the reciprocal of cosine of 2.1274. So this is 1 over negative 0.52828. Then finally, cotangent of 2.1274 is the reciprocal of the tangent of 2.1274, or I can think about it now as cosine over sine. So this is going to be negative 0.52828 divided by 0.84907. So cool, we've satisfied the definitions to evaluate these 6 trigonometric functions, but that's not particularly interesting to us. Let's think about something a little bit more useful, perhaps. So the most important property of the unit circle is in its name. It's the word unit. And so wherever we go, the radius of this circle is 1. So if we look at this point of intersection with the unit circle, then we can say this forms a right triangle with legs that have x and y as their lengths. And so by the Pythagorean theorem, we could say x squared plus y squared equals 1 squared. And in fact, this is the equation of that circle. But how do we understand this in the context of trigonometric functions? Well, if this is an angle t, then the x and the y coordinates correspond to cosine of t and sine of t, respectively. So I could write this as cosine of t, and then square that number, and then I could write sine of t, and then square that number, and that's equal to 1. And it turns out this is always equal to 1. We call this the Pythagorean identity. So I'm just going to write this right here, Pythagorean identity. And so we realize that's way too many parentheses to be writing on a regular basis, so we agree on a notation that's shorter, and it means this. We write the following. Cosine, and we put the exponent right there, and then put the argument t afterward. Sine, we write the exponent right there, put the argument afterward. And we read this as cosine squared t plus sine squared t equals 1. This notation means find the cosine of the angle, get that number, and then square it. And something that's worth noting, in these calculators, if you would like to do this, for example, if I want to take cosine of an angle, let's imagine 1.2, okay, and I want to take that value and square it, I would have to type cosine of 1.2 and put the exponent afterward. If I try to do something ridiculous like cosine, put the exponent here and then type 1.2, the calculator won't understand what I mean by that. So make sure we understand that this is what we write, but in the calculator, we would have to write it like this, as though we have the original notation. And then, just for good measure, let's check to see if this identity holds for the angle 1.2 radians. Let's just try it. Oh, it's exactly 1. But of course, because everywhere on the circle, x squared plus y squared equals 1. Now, while we're here, let's also consider 2 variations of this. So I'm going to write down cosine squared t plus sine squared t equals 1. And I'm going to take this and say, why don't I divide both sides by cosine squared t? As long as cosine of t is not equal to 0, then I have preserved the identity. So then I say, in terms of fractions, I can say cosine squared divided by cosine squared is simply 1. And then sine squared divided by cosine squared, I could write this as sine of t divided by cosine of t, and this whole thing is squared. And over here, I could write this as 1 over cosine of t, and this is squared. But then I remember that this is actually tangent of t. So I would write 1 plus tangent of t squared, and I would remember this as the reciprocal of cosine is secant, so I could write this as secant of t squared. And for shorthand, we would write 1 plus tangent squared t equals secant squared t. This is the same as that, with perhaps the caveat that cosine of t cannot equal 0 in this version, but this, once again, is a Pythagorean identity. We have two of these. Let's try one more variation. Let's take cosine squared t plus sine squared t equals 1, the original Pythagorean identity. And this time, let's divide both sides by sine squared of t. So we would argue the caveat now is that sine of t cannot equal 0. So fractions, cosine squared divided by sine squared is cosine of t divided by sine of t, and this is squared. Then sine squared divided by sine squared is simply 1, and over here on the right, 1 divided by sine squared, I can write as 1 over sine of t and square that. This we recognize as the reciprocal of tangent, also known as cotangent. So this is now cotangent of t squared plus 1 equals, this is the reciprocal of sine, which is cosecant, so cosecant of t. We'll square this, and then we'll write this in shorthand. So cotangent squared t plus 1 equals cosecant squared t. The three identities written in red are all Pythagorean identities. These are worth remembering. This for sure. This very useful. This a little bit less common because in most cases you can just use this one or that one, but all very useful. Now let's imagine a scenario in which you know that sine of a certain angle is 2/3 and cosine of that same angle is the square root of 5 over 3. Now at this stage in our life, we don't know exactly how to find the angle t. We're not concerned about that, although perhaps we could produce a quick sketch and say the angle t is some interesting place where the y-coordinate is 2/3 and the x-coordinate is root 5 over 3. So we could say maybe over here, this is root 5 over 3, comma 2/3, and we understand that the angle t is the one right there. Okay. What would we like to do with this? Let's say our goal is to find the values of the other trigonometric functions. Well, we know that tangent of this angle t is going to be sine of the angle t divided by cosine of the angle t, which for us is simply going to be 2/3 divided by square root of 5 over 3. And if we simplify this down and rationalize the denominator, we should end up with 2 root 5 over 5. Well, it's a number. If we want to know cosecant of t, we would say this, by definition, is the reciprocal of sine of t, which means this is 1 over 2/3, also known as 3/2. We can say secant t is 1 over cosine of t, because secant is the reciprocal of cosine, and that will be 1 over root 5 divided by 3, and that, if we rationalize the denominator, should turn out to be this. We can also finish out with cotangent of t is the reciprocal of tangent, so we might as well just say 1 over tangent of t, which would be the reciprocal of this, simply square root 5 over 2. So they're all numbers. Are they cool numbers? Maybe not. But the point is, if you know the values of sine and cosine, you can find the values of every other trigonometric function. Or perhaps, if you were not given these two, but you were given some other two of them, as long as those were not reciprocals of each other, perhaps we could find all of the others by the same method. Let's imagine another scenario where we are given sine of an angle t is 1/2, and 0 is less than t is less than pi over 2. So what that means to us, if we quickly sketch this, we know that the angle t is between 0 and pi over 2. So we know we're in the first quadrant. And then we know that the sine, meaning the y-coordinate, is 1/2. So we know we're over here somewhere. This angle is t. And we don't know the x-coordinate, but we do know the y-coordinate is 1/2. And what we would like to do is find the values of the other trig functions. Well, this time we only have one value, but perhaps we can invoke a Pythagorean identity saying that the hypotenuse is 1. We could write down sine squared t plus cosine squared t equals 1. And then we would substitute, this is 1/2 squared plus cosine squared t equals 1. Subtract the 1/4, we'd get cosine squared t equals 3/4. Then square root both sides, we get cosine of t is potentially plus or minus root 3 over 2. But this is where this information comes in. Our picture and this confirm that since the angle is in the first quadrant, the x-coordinate of this point must be positive, which means we cannot accept the negative version of this. We must say this is root 3 over 2 positive. And once we have this, we can find the values of all the other trigonometric functions by saying tangent of t is simply sine of t over cosine of t, which for us will be, sorry, I pointed the wrong thing, up here 1/2 for the sine of t, divided by root 3 over 2 for the cosine of t. This will turn into root 3 over 3 when you rationalize the denominator. Cosecant of t is the reciprocal of sine of t. So that would be 1 over 1/2, hence 2. We'd say secant of t is the reciprocal of cosine t. So that would be the reciprocal of root 3 over 2. When you rationalize the denominator, that turns into 2 root 3 over 3. And the last one, cotangent of t, is going to be 1 over the tangent of t, which is going to be the reciprocal of this, simply root 3. So here we go. We have it again. So now this time, we only had one trigonometric function, but we had which quadrant we were in. Incidentally, this is enough information to find the values of all of the trigonometric functions. Now, let's discuss a cool property of trig functions. In this case, we have a familiar angle, and we have a familiar intersection point. We know that cosine of pi over 6 is root 3 over 2. We know that sine of pi over 6 is 1/2. But what if we asked about coterminal angles, which you remember from section 4.1 are angles that have the same terminal side. So if I were to take the angle pi over 6 and add 2 pi to it, that would be taking an extra circle and adding it to this angle. 13 pi over 6 should end up in the same angular position as this, meaning it's going to have the same intersection point, right? Because it's just pi over 6 plus an additional 2 pi. So if I asked, what is cosine of 13 pi over 6? Well, that would be the same x-coordinate of the same intersection point because we have the same terminal side, root 3 over 2. If I ask for sine of 13 pi over 6, I would get the y-coordinate of the same intersection point for the same terminal side. And so this allows us to say that if we go around the circle and end up at the same terminal side, we get the same intersection point, which means we get the same values for the trigonometric functions. We can say that for any angle t, if we add 2 pi to that angle, meaning we have a coterminal angle, then we get the same value for sine as the original angle. Same thing with cosine. Cosine of t plus 2 pi, this is coterminal with t, so the value is the same as cosine of regular t. This property, we say a periodic function is a function such that f of x plus some constant p is equal to f of x for all values of x. And technically x and x plus p in the domain, if we want to get real technical here. So this p is a constant. And we say the smallest constant p for which this relationship is true is the period of f. So that means how often the values of this function repeat themselves, that is the period p. So in this case, if you go around the circle once, every 2 pi radians you go around, you're going to repeat the sine and cosine values exactly because you're hitting the same terminal side, same intersection point. This 2 pi is going to be the period of sine and of cosine. And incidentally, of cosecant and secant. Because we can say cosecant of t plus 2 pi is simply the reciprocal of sine of t plus 2 pi, which by this property we understand is simply 1 over sine of t, which then we understand is equal cosecant of regular t. So evidently cosecant has this same property. Same with secant. Secant of t plus 2 pi, which is 1 over cosine of t plus 2 pi. And by using this property, we can say this is the same thing as 1 over cosine of regular t, because cosine is periodic with period 2 pi. We can finally conclude that this is the same as secant of regular t, and hence secant also has a period of 2 pi. So we might ask, what about tangent and cotangent? Are they periodic too? Well, they're based off of sine and cosine. Those are periodic, so tangent and cotangent are also periodic. But they're a little bit special. They repeat more than once per circle. So here's what I want us to think about. If I look at tangent of the angle t, then this would be y over x based on this intersection point, which if we were to think about this triangle here, y and x, we can also think about y over x as the rise over the run for this line. Indeed, if you look at the unit circle, then tangent of an angle is the same as the slope of the terminal side in the unit circle. And so then we ask ourselves, how often does tangent t repeat itself? Meaning, how often does the slope achieve the same value? Well, the easiest answer is, let's continue this over here and say, oh, there's an angle if I go to that terminal side where the slope is the same, and therefore the value of tangent is the same. And you can tell because x is going to turn into a negative value, y is going to turn into a negative value, but this will ultimately be negative x comma negative y. When you take this value divided by that value, the negatives cancel and you get the same overall tangent. So it turns out that this difference is half a circle, so we would say this angle is t plus pi. And so tangent is special because tangent of t plus pi is the same thing as tangent of t. And since cotangent is the reciprocal of this, we can write cotangent of t plus pi, which is 1 over tangent of t plus pi. By this property, we can say this is the same thing as 1 over tangent of regular t, and then by the reciprocal property, we can turn around and say this is cotangent of regular t. So we say, overall, sine, cosine, cosecant, and secant have period 2 pi, and tangent and cotangent have period of pi. And this distinction will become very, very important when we graph these functions. So it turns out this idea is really useful. Because we have here a familiar angle pi over 3, and we know that cosine of pi over 3 is the x-coordinate 1/2, and that sine of pi over 3 is the y-coordinate root 3 over 2. And because we know that cosine and sine are periodic with period 2 pi, we can add 2 pi to the angle, get a coterminal angle, and say cosine of 7 pi over 3, if I add 2 pi, is the same as cosine of pi over 3. Same deal with sine. Sine of 7 pi over 3 is the same as sine of pi over 3. I can add 2 pi again. I can say cosine of 13 pi over 3 is the same as cosine of pi over 3. Sine of 13 pi over 3 is the same as sine of pi over 3. And I can go backwards, subtract 2 pi, say cosine of negative 5 pi over 3 is the same as cosine of pi over 3. Sine of negative 5 pi over 3 is the same as sine of pi over 3. And so the conclusion is, if we can find the values of cosine and sine, so the x and y coordinates of all of these points for one lap around the circle, so between an angle of 0 and 2 pi, then we can use that information to find the sine and cosine for any angle, any real value of t. And so there we have it. That's the end of section 4.2. Thanks for tuning in. I'll see you next time.